Okay, so I'm going to tell you today about scalars and vectors, and really the first one is probably a concept that you already know, but only with more fancy terminology. So what do I mean by? Let me start with with what scalars are supposed to be. So as I was saying, scalar is when you say that something is a scalar, it's just a new name for saying that something is a real number. So you should think of a scalar as a real number. Okay, and so the quintessential examples of scalars say are, for example, temperature, speed, distance, mass, also pressure, like air pressure. Okay, and so for example, each of these are measured with just a number, maybe followed say by a unit. Right, so temperature, you could say 50 Fahrenheit. So just like the number 50 followed by some unit. Speed, 30 miles per hour. Distance, say between 2 points, again like maybe in feet or miles. Mass in pounds. Pressure, I guess, pascals, I believe. But the point of each of these quantities, right, is that in order to specify them, you just need a single piece of information. So just need to specify it. One of the reasons why you might call this a scalar and not just like say a number is that usually you also want to think of scalars as quantities that everyone who measures them will agree on the value that you are supposed to get. So for example, temperature, if I measure the temperature right now here and someone else measures the temperature simultaneously at the same place, the point of a scalar is that we should both agree on the value that we get. So we should both agree that at this location, at this time, we're measuring say 50 Fahrenheit. Okay? And the same with other quantities. So say with mass, like the idea is that if you measure the mass of an object and another person measures the mass of the same object, if it's done simultaneously, they would both agree on the measurement. And so the others are, well, yeah, basically that's like the philosophy, although you have to be a bit more careful. And I may say that a little bit later. But for now, the only thing that you have to really think about is that in order to specify a scalar, you only need to know a certain quantity. So it's like an amount of something, okay? On the other hand, vectors, which again, you probably already know, they need more than just a number. They also need a direction. So what's the point of a vector? So in order to specify them, so if you want to determine what a vector is, you need a number. Let me just write it like this. You need a couple of things. You need a number, or also a scalar if you want to use the terminology that I just presented. So you need a number that tells you how the magnitude of the vector, okay? And so at this point, a vector is not different from a scalar. What makes it different is, and this is the key information, you also need a direction for the vector. So you need so a vector consists of two pieces of data, which a number together with a direction, and that's why you'll usually think or are told that you can think of vectors as being depicted by arrows. Okay, so you want to think of them as, and this is like a useful idea throughout the course, is you think of them as arrows. Okay, so here you go. This is a vector. Right, so the magnitude of the vector is just like the size of these arrows, so the magnitude is the size. And well, the orientation where it's pointing is the second piece of data. So basically, what I'm trying to say is that this is a vector, right, of certain size, pointing in certain direction. This is another vector of the same size, but now it's pointing in a different direction. In fact, one that's perpendicular to the one that I just used at the beginning, which means that these two vectors will be regarded as different vectors despite the fact that they have the same magnitude. So let me just maybe point this out here. So for example, so these two have same size, or again magnitude, or norm. Well, that's another name that I'll use later, but different directions. So these are not regarded as the same. So not the same. On the other hand, one could do something slightly different, which is just take this one and make copies of it. So by that I just mean you copy paste it throughout the plane. Okay, so again, imagine that all of them, I just took my vector and put it here, 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 here. Okay, and so now all these vectors, they have the same size, right? So let me put so same size, and they also point in the same direction. So same direction. So these vectors will be regarded the same. Okay, so these vectors will be considered regarded as the same vector. And so what that means is that you're you're free to move a vector around the plane. So as long So the moral of this example is that the key idea is that you can move a vector. So you can move a vector and it will be considered the same as long as you don't change its magnitude nor orientation. Okay, and actually this will be useful soon, because that means that, say if you have this vector here, then you're free to move it to this spot, right? I didn't change its size nor orientation, so this is the same as this vector. But now I want to think of this conveniently for boards, so you want to think of this as the y-axis and this as the x-axis, and so that means that you can think of this vector after the displacement. You can think of this vector as a vector that starts at the origin of a coordinate system that you're using. And once you do that, you can identify this vector with the point where this vector ends, and that's how you will think of this vector as a position vector. And so that means that, let me say this more explicitly. So in particular, let's see. So that means that in particular, if you choose a coordinate system, say x, y, if you had this vector here, which by the way, I guess is a good moment to use some notation. So a vector, vector, let's call this v. Okay, in order to remind yourself so that you can distinguish it, say, from an ordinary number or variable, you sort of tend to put like an arrow on top of it. Okay, if you read a book, they may not use an arrow, they may just write it in boldface, so bold letters. So that's like the other way which you will see it, which is difficult to make on the board. So for usually on the board, I will put always an arrow on top of them. And so what I'm saying is that you're free to move it, and once you move this, again, since this is being regarded as the same vector, I'll just put it like this. But now, when you think of this as a in this standard position, now you can think of this vector as singling out a point in space. So when you move a vector so that it starts at the origin, it will specify a point in space. And so you think of this vector now in this way as a position vector. So, and you think of it And once you do that, I mean, you could still call it v. It's just that it will get a little bit confusing because typically you think of vectors, say you think of v as being velocity, so you psychologically change its name. Again, you're always free to baptize a vector with whatever letter you prefer. And so now I'll think of it as a position vector, and let me just forget about this already. And so this will be like the position vector of the point P, which has coordinates x, y. And if you want to even emphasize more the fact that it's the position vector of this point, you'll write r sub p. Okay? And so if you had another point Q, which has coordinates AB, then there will be, say here, another position vector, which I will now call R sub Q. Okay? And so what this is already suggesting is that there are quantities which you already knew, which naturally qualify as vectors. So in the same way which I gave you like a list of scalars, you could think of a list of vectors. So again, there's like a position vector, there's a velocity vector, there's an acceleration vector, right? There are others, force, for example, you also think of it as a vector. There are others which you may be less familiarized with, but say you can think of, say, something like the electric field as a vector. You could also think of a magnetic field which as a vector, which we will discuss near the end of the course. And so the point is that any of these entities, in order to fully understand them, you have to tell me, in addition to a number, you have to tell me like a direction at which they're pointing. Okay? So in the next video, what I'll do is just explain to you sort of what you can do to vectors, right? So with numbers, you know, like for example, you can add numbers, you can multiply numbers, you can sometimes divide numbers as long as the denominator is 0, right? You can take square roots of numbers. Well, some of these operations have analogs in terms for vectors. Not all of them work, but still, we'll see that now they sort of have like a nice geometric interpretation.